Good morning.
Guten Morgen.
Okay, is everybody see my slide?
Yes.
Okay, perfect. Okay, so what we've done on Friday was we were looking at what we call level pool routing methods. And essentially what the idea is to be able to have an inflow into a reservoir and predict the outflow. And again, this is all driven by the fact that when you have some large water body or you have a small water body like Burwan Park, there's going to be an attenuation of that hydrograph from the upstream end to the downstream end is going to be totally different because of the storage effects of the reservoir. And so we've had this process, and we're going to use what's called level pool routing, or also known as reservoir routing, to solve basically this equation here, which is looking at the storage, the outflow, and the inflow to come up with the outflow hydrograph. The inflow hydrograph is driven, or basically it's the I. The storage is what is stored at each time step. And so at the previous time step, which is designated J, you know the storage, you know the outflow, you know the inflow. At the J+1 time step, you know the inflow because that's the boundary condition. You're given an inflow hydrograph through time because we have gotten that by some means. In the case that what you've learned how to use the unit hydrograph method to model. So we've got an inflow versus time hydrograph. So we know all the time discrete values through time of what that inflow looks like. So J+1, J+2, etc. And so when we solve this hydrologic routing equation, we notice that the unknowns here at the J+1 time step are both the outflow and the storage. So we talked about we have to go through and come up with a relationship called the outflow storage outflow function relationship, this right here. And the way we come up with that is we have some relation between elevation of the reservoir and storage, which is the S value, and elevation of the reservoir and outflow, which is the Q value. And we can put those together for like values of elevation. We can know what the outflow is and what the storage is. So we can build a relationship between Q and this storage outflow function, which is the 2 times the storage divided by delta T plus Q. So the thing here in this model, we have to know when we do our storage, our level pool routing, our reservoir routing method, we have to specify a delta T, which is the time step of the model. And so these are independently derived. The rating curve for the outflow and the elevation storage curve, those are independently derived, but they're derived from information that we can know. If we have a weir at the outflow end of the reservoir, we can easily come up with a relationship between elevation and the outflow discharge. You remember that for the weir, Q is equal to CB H to the 3/2. We did that in lecture 19. And so the C was a coefficient of discharge. The B was the width of the weir, and the H was the head. And so you have some weir that, let's say that we had a sharp crested weir and the water was going over that. The H value, that was the H, especially if you had the velocity head on top of that. That was our H. The width, obviously self-explanatory, is how wide that is. And then the coefficient of discharge, remember I talked about there was an entire methodology you could go through. The USGS has an entire not textbook, but report on deriving the values of the coefficient of discharge for weirs. And there's other manuals for that as well. So I wouldn't hold you responsible for, doing all the things necessary to get the C value for a quiz or an exam. But I might give you, this is a sharp crested weir with a value of coefficient of discharge of, 3.6, and the width is, 10 feet. And so then you would go through and you'd figure out a relationship between the elevation and the discharge. The storage versus elevation curve, when we think about that, you'd have to have some sort of surveyed data. The example problem we're going to work here in a second, I tell you, you got a 2-acre reservoir with vertical sidewalls. So we know that the bottom surface of that reservoir is 2 times 43,560 square feet, right? So you've got 2 acres. An acre is 43,560 square feet. And so then, you can come up with a relationship between the elevation, assuming the bottom of the reservoir is 0, and the storage that goes in it with each successive amount of elevation you add. You can come up with a storage curve. And then taking that data between these two graphs, we can come up with this relation. And that's what we're going to work through in the example problem. So let's talk about our example problem. We've got a 2-acre stormwater detention basin with vertical sidewalls. The inflow hydrograph is given as a triangular hydrograph. We can think of that as something that comes from maybe a simple NRCS triangular synthetic unit hydrograph method. Maybe it only had 1 increment of rain or something very simple. What we want to do is route the inflow hydrograph through the detention basin using an elevation outflow relation for a 5-foot diameter pipe spillway that lies flush with the bottom of the detention basin. So what I mean there is I've got some detention basin here, so water comes into it, and in the very bottom of this detention basin, I've got this 5-foot pipe that allows water as it stays in there to outflow through that pipe. And so I also tell you, assume the basin is initially empty, use the level pool routing method or the reservoir routing method with a 10-minute time step to determine the outflow hydrograph. So the question I've got there is, what is the maximum elevation in the basin? It's kind of a question that would say, well, how high do the walls need to be? So if you assumed them infinitely high, obviously you can't build them that high. How high would these be if we had a 2-foot acre stormwater detention basin? So this is the data for the inflow hydrograph. This is data that I'm going to switch over to a spreadsheet in a second, but this basically says at the upstream end of this reservoir, this 2-acre reservoir, this is what the flows look like on the upstream end. You can see it goes from 0 at time equals to 0 up to 60 CFS and then back down to 0 in a fairly short order. This is our outflow storage. This is our outflow versus elevation rating curve, and this would I've given to you, and this is an elevation storage curve which we will derive. This is going to be given because you don't know enough to know what the flow looks like through that pipe. If I didn't give you a weir in this case, so I'm not telling you to derive this from scratch, and then we end up taking these two together to get this outflow storage function relationship, and we're going to talk about how to get this. So I'm going to switch over now to the spreadsheet and go from there. And so we've got basically let's see here, I want to get rid of this, close that off. And here's our given. So we've got the delta T here equal to 10 minutes. And so this is my delta T. And here is given to us the outflow discharge versus elevation. This is what flows through that pipe for every foot of elevation up to a maximum value of 5 feet. And this is the storage. And this is basically very easy to compute. At 1 foot of elevation in the reservoir, I've got what? I've got 2 acres times 43,560 square foot in an acre times 1 foot of water in that, because the elevation at the very bottom of the reservoir I've told you is equal to 0. That equals to this 87,120. And then the same thing for the next one. I just went up 2 feet, then I went to 3 feet, etc. Well, when I start to develop all this stuff, this is my given. I'm going to have much more detail in how to come up with these various, this outflow storage relationship. So I'm going to then take and make this a little bit more detailed. I'm going to have to interpolate between 0 for an elevation and 1 feet of.
Can you scroll up for just a second? Sorry, I'm trying to get the data thing that you just had up there. Trying to follow along.
You're trying to do what? You want me to, you want to show this here? I'm sorry, you cut out if you're trying to tell me something. No, I'll assume you're okay then. All right, so basically we're gonna interpolate between where I actually have data points here. And so all this is, this outflow discharge is just simply an interpolated value between the value of 0 and 1. And here very early on, I had to, do some finagling to get this to not be a negative number and make sense here at the very lower flow. So you can see for an outflow or for an elevation of 0.24, I'm saying that the outflow discharge is 0.53. That's just an interpolated value between discharge of 0 at an elevation of 0 and a discharge of 8 CFS at an elevation of 1 foot. Okay. Then I move over to the storage. So this column here, column A, is just basically the elevation in the reservoir. Column B is just the outflow discharge, which is just turning this relation here of elevation versus outflow into a more detailed by every 100th of a foot value of discharge. And then the same thing is done with storage, which is simply basically looking at, here I don't even have to interpolate because I know that we've got, if you look at the equation here at this end right here, you can see that I'm just multiplying 2 times 43,560. That's 2 acres times 43,560 square feet in an acre, and then I multiply it by the elevation. And that gives me the volume of the storage. And you can see on that particular case for 0.01 foot of water in there, I've got 871 cubic feet of water. And then in order to come up with the value of what we call the storage outflow function, it's just a matter for every elevation here, I've got a value for the outflow discharge and a value for the storage. And then I can put those together knowing that delta T is equal to 10 minutes. And I convert that over into seconds, by the way. And I can then go and calculate what that is. So you can see the equation up here at the top. It's just basically 2 times the value of S, which is incorporated in column C, divided by the delta T, which again, I said I have to convert to minutes or seconds. So that's 10 minutes times 60 seconds per minute. And then I add the outflow value, which is in column B. So you can see that for the particular elevation of 0.01 feet, I've got an outflow storage function here of 2.914 as our value. And that has units of cubic feet per second because that's just the units on this equation. Doesn't mean that it's an outflow, it just has that as the units. So then this is the storage outflow relationship that we are talking about here. I just plot that data. Again, if I go back to the PowerPoint slide, you can see that this is what we had. We have the outflow versus elevation, the rating curve. We have the elevation versus the storage curve. We combine those two like I've just done in the table, and we come up with an outflow versus storage function. And that's what you see there. All right, so as we go over and you look at this, then I want to have a lookup ability in this, and so I just repeat the values in here and just rearrange them in terms of discharge, storage, and elevation. So if I've got a value of discharge here, I can go and get a commensurate value of the storage. And I'm just restating those. It just makes it easier later when I start the modeling process. So up here in the top, this is the modeling. This is going to be the level pool model that we use here. And so let's just kind of go through this. The first column here, column L, is the time, and it's in minutes. And so you'll notice that I gave you an inflow hydrograph. This is given to you, or you might have derived it using unit hydrograph methods or something like that. But this is, in this particular problem, is given. So you can see it goes up to a maximum value of 60 CFS at 60 minutes into the storm, down to a value of 0 at 180 minutes, okay? And so let me rewrite on this problem. Let's go over and get the equation that we're dealing with. So here's our equation. I'm just going to copy this over at the top, and we'll just place it right here. So this is what I'm trying to solve. And so you'll notice that the first thing I'm going to get is I get the value of ij plus ij plus 1. And so in this particular instance here, when I'm at this point right here, trouble picking on that. Okay, so when I'm in cell N9 there, the j plus 1 time step, let's just highlight these, is the one I'm on, and the previous time step is the j. So you can see that I'm just adding the ij plus 1 would be 10, the ij is equal to 0, because I'm modeling, you know, I'm on this row 9, this is where I'm modeling. I'm trying to get at a storage value and essentially a qj plus 1 value for that time step, okay? And so the first order of business is calculating an ij plus 1. Then I go through and say, okay, what is this aspect here, the 2s at the previous time step j over delta t minus the outflow at the previous time step j. So you'll notice here, I'm on this cell, which is in column O, which says, okay, 2 times R8, R is the value of the storage at the previous time step. You'll note that's 0. So you can see that R8 is 0 for the storage, divided by delta T, which is the 10 times 60, minus the Q8, which is the outflow at the previous time step, which was 0, okay? And so now I have that element. And then once I've got that, I go to the next column, which is P, which is going to basically be this calculation of the 2s the j plus 1 time step divided by delta t plus the outflow at the j plus 1 time step. So this is this value right here, and you'll just notice when we look at that, all that is adding the column value in that row from column N, which is the value of the ij plus 1, and then the 2sj over delta t minus qj, that's contained in column O. And so we solve for that. At that point, then we've got this value, and now we can go, as I told you, back to our storage outflow function versus Q, and we can get at a value of that. And I use a VLOOKUP function, and a lot of students aren't that familiar with it. So let me explain this really quickly. The VLOOKUP says, okay, that's a function in Excel that says automatically it's going to look at a table. And the first item here is P9. So it says, hey, look at a table that's contained in this area right here, the D, and you have to use the absolute, the dollar signs to get an absolute cell reference. And so that's absolute cell D26 through E26. And so what that is you can see it highlighted here in red. That's this basically the area we've developed here when I developed this outflow storage relationship. I'm sorry, the storage outflow function versus discharge relationship. And so it goes in here and says, okay, here's my table. It says, look at the value in P9, which is a value of 10, and says, go down to this table and then use the second column. So it goes through and looks for a value of 10. And so you can see here that it's going to find the last one prior. So there's not really a value of 10 in here. Let me see if I can still do this. It doesn't have a value of 10, but it has a value between 8.722 and 11.626. And the way Excel works in these lookup tables is it will get the previous one. So it's going to say, okay, well, we don't have a value of 10, so go back to 8.722. And this is a two-column table. And remember, the function said, look at the second row here. And so, or I'm sorry, second column. So it returns the value in that second column. So it returns this 0.01. And you'll notice that's the value that you see here in this table. So that says at that time step, 10 minutes in, now the outflow is 0.01. And then I can also go and say, hey, what's the storage? The storage in that is a value of 5,227.2 feet. And then I can also go through, you know, I picked that up from that same kind of lookup function. It just looks at the discharge and then gets the commensurate storage value for that. And then I can do the same thing in getting the elevation inside the reservoir. I use a lookup function there too. Says, okay, well, when the storage is equal to 5,227 cubic feet, what is the elevation that corresponds to that? And it goes down the table and it gives me an elevation. And then I move into the next. And at these low values, you're going to have some oscillation here because numerically these are very sensitive. You don't have very much depth, and so there can be some easy errors to make here, and you have to kind of watch this and make sure these errors don't propagate. So I move to the next time step, which is time is equal to 20 minutes, and that now becomes the J+1 in our equation up here. The previous time step becomes the J time step. So now we're going in and we're looking at the same thing, and we now have the inflow, which is given to you. So that's a boundary condition. The IJ plus 1, if you'll notice on that, is just basically the inflow of the current time step we're on, which is J+1, minus or plus the inflow of the previous time step, which is 10 CFS. And you add those two together, that becomes 30. We look at the previous time step and we calculate this 2SJ over delta T minus QJ, and that becomes the 17.414 value. And then we basically add those two together in that column P. We get 47.414. We go to our lookup table and say, okay, what is that in terms of, let me delete that. What is that in terms of a value of discharge? It goes to the lookup table again. It says, okay, go to this table. Again, the reference is absolute reference D26 all the way to E26. So it's a two-column table. And it says, okay, look over in cell P10. What is that value? Oh, that value is 47.414. Now go to that table, look in the first column, and when I look through that first column, find the nearest value to 47.414, and then look over in column 2 and tell me what corresponds to that. And that's what you've got there is the 0.03 cubic feet per second. And then from that, we've got an outflow value. I can go back and I can say, what does that correspond to in terms of storage? And then what does that correspond to in terms of elevation? And then I just keep repeating that. And the question I had for the problem, if you remember, is what is the maximum elevation in the reservoir? And you can see that we get down here through the process and we have 1.95 feet is our maximum elevation. So I plot this data and you can see what it looks like here. And so in blue, the blue dots are the inflow hydrograph. The red dots, or red squares, are the outflow hydrograph. And the storage amount is in green, and you can see that is in cubic feet. And you can see we hit that maximum storage about 120 minutes into the storm event. And you can see we really knocked the outflow down by, even with that big a pipe, that's a huge pipe, 5 feet in diameter. Even with that big pipe, we're able to attenuate that runoff storm from 60 CFS down to 30 CFS. So that is today's example of a level pool routing exercise. Are there any questions about this? I'm sure there are.
Could you like share that spreadsheet so we could like look through it at our own pace?
Yeah, well, if you attended the lecture on Friday, I asked you to look at this problem. I told you it was on Canvas. This example, this Excel problem is already on Canvas.
Okay, sorry, I just forgot about that.
Yeah.
Dr. Holmes?
Yes.
So I was looking over the first table with the elevations, the outflow, discharge, and the storage. And I know that the elevation and the discharge outflow is kind of like an interpolation from the original data. What I'm kind of confused about though is for your 1 foot elevation, your outflow for it is 10.63, but shouldn't it be 8 if it's an interpolation?
Right. Yeah, that's a little bit of the problem with trying to do the interpolation. As I said, there's a little bit of instability. There may be, that may have been some error that I didn't take care of here. So let me look at that. So if I've got an outflow discharge for elevation of 1, let's see what happened here. Yeah, it looks like something got a little bit iry on that. I'm gonna have to look at that. There may be a mistake in the spreadsheet. That's a great catch. Let me look at that. I've got various versions of this over time that we've used and students have played with it, and I may not have corrected back. I think this one last year, I was actually in the class doing this one on the fly, and we were adjusting things because you get some, when you do an interpolation, you can get some funny numbers going, especially early on, and so we were tinkering with that a bit. Let me look at that if you don't mind. Let me see what I did here. Let's get down here. What am I? Goes to J50, J. It's looking at I. Yeah, I might have to look at how we've got that value. I think what I did is I fitted a, okay, you see this, what I've done here is I fitted a best fit curve. Now I remember what I did to do this quickly in class last year was I took the values, and you see this, right? Are you able to see my cursor?
Yeah, we can see it.
Yeah, so what I did was I fitted a curve through this, a power curve through the data. See that 3.9286 x squared plus 8.4143x minus 1.7143. And so in order to expedite this quickly, because I think we had some problems with this last year, I went ahead and fitted a power curve through that really quickly. And so you notice it doesn't fit it totally. And so it's, there's an R squared up there fitting that curve of 0.9987. So it's not going to exactly fit. And you can see that, even in the plot here, it overestimates. Let me pull up my pen. You can see the plot that the curve, the black line is right above at 1 foot is right above the 8 CFS. And so we're overestimating it at 10.63. That makes sense? In essence, I didn't interpolate between the two. I originally did, and I had some problems with that. So I went back and did a power curve fit. So in
Okay.
this, yeah, so in this particular case, the 1 foot is now 10.63. So, you know, we're saying, okay, well, we're going to call it 10.63 instead of 8. We use these where maybe this was measured data where I had some measurements, and we know there's error in the measurements, and so this is our best fit through that. Hope that makes sense and doesn't throw you off too much. Does that make sense?
Yeah, it makes sense.
Okay, good. Other questions? Good eyes, though. Appreciate that.
When you are developing your reservoir routing table on the right, when you're developing doing all the lookups, why wouldn't we look up everything with respect to the 2s over dt plus q column?
You talking about the P column?
For the subsequent ones where, so like when you're doing the lookup for the q j plus 1, the sj plus 1, and then the elevation, the sj plus 1 and the elevation ones you look up with respect, I believe, to the q j plus 1 column.
Oh, you could have. You talking about in terms of the Q and the R column?
Yeah.
Yeah, I could have went off this to get the Q, S, and elevation. You could have.
Okay.
Yeah, you know, take the spreadsheet and play with it and see if it works out that way. I think it was just, I don't know why I did it that way, other than just to give experience to the students looking at when I was putting this together last year.
Okay.
Yeah, just try it and see. I mean, the best way to learn is to try to bust stuff and try to get into the guts of it. I really think that's a great way to say, oh, could I have done this differently, or, you know, try to find errors. I encourage you. I mean, you know, a lot of these examples sometimes I put together for students on the fly, and there could be error. I mean, there could be errors. Now, not the equations are right? So this is the correct equation. And there are other ways in Excel to probably pull up these numbers rather than VLOOKUPs, and I don't know what they are, but I mean, you could fit maybe a curve through this functionality here and come up with a curve or something. You know, it's just smoother for me. I use VLOOKUPs all the time when I'm using Excel to work on little problems like this. Great questions. What else?
Dr. Holmes, Alyssa's question was really good because I noticed that too, of like when you're trying to interpolate all of that. So would you recommend us using that power fitting equation to solve for that? Or
you're talking about for the outflow relation, or you're talking about to compute this column right here?
For the outflow discharge.
Yeah. Well, no, I mean, are you talking about fitting this line right here?
Yeah. Mm-hmm.
Yeah, I mean, I don't think there's anything wrong with that, because, you know, that's essentially, we don't fit a power curve through data at the USGS, but we will fit a line through our data that best fits, because you get data plotting, like a real data in the real world kind of plots like this. So you just can't make a zigzag line. You know, you're not going to do that. So we do some sort of best fit. A lot of times it's an eyeball a trend through the data. We do have sophisticated programs that look for, you know, best fit lines and stuff like that, you know, from a like a least squares type of approach or something like that. But often it's these rating curves are built based on these, you know, kind of the best fit through the line.
Okay, thank you.
So to give you some incentive to understand this, we're going to have a quiz on Friday, and I'm going to give you a problem very similar to this. You're going to have a level pool routing problem, and you're going to, you know, you can do it by hand. It's going to be a pain, but I would suggest that you figure out spreadsheets and know that, you know, I'll give you some element of this, and we're going to see if you can, you know, don't just copy my spreadsheet verbatim. You know, you need to be able to work this out on your own, because if you just try to mimic mine as a template, I mean, it's fine to use as a template to learn, but if you don't understand the mechanics of this, depending on how I ask the problem, you may be lost. Okay, so I encourage you to learn it, and then we'll have a quiz on Friday that I'll give you a problem using the level pool routing method. Questions?
Is that gonna be the last quiz?
Yeah, what do you want to do that as a last quiz, or you want something else?
I mean, if we can skip this question and move, talk another one, that would be more better. And this problem.
Well, you're gonna have this as a problem. Sorry.
Dr. Holmes.
Yes.
Sorry, I have another question. So, you have in like one of your notes that above elevation 0.28 feet, the outflow is using a different equation, but in your calculations of the outflow discharge, you still use the same fitting equation that you had. You have it in cells I2 through I4.
So let me see what you're talking about here. So would that be, you're talking about the worked out problem in the, I'm trying to think here.
No, it's in your notes. I think it starts in cell, oops. Sorry, I'm adding stuff to a different equation line. I think it's in D24.
B24.
Elevation. So it looks like there's another equation that was used.
Okay, are we in column B or your column
It's
D?
the note in D24. So you're up, like, it's a note.
Oh, okay, above elevation. Yeah, so let's see here. Let's see what we've got.
Because in those you don't have like a function, but once you get to a function, you're using the equation that you used from the table and not this equation. So I was just wondering what this equation was.
Yeah, so that was just kind of, I think what I did was, in fact, it's above, it looks like to me, it's above elevation 0.18. Yeah. So this should be corrected to 0.18. And then this below that was just interpolated between what I had at 0.18, which is 0.03. And again, this is going to make so little difference, this low end, at the beginning of the problem. It's not going to add a lot to the,
Overall.
yeah, I mean, think of it. Think of what 1/100 of a foot of water looks like. It's pretty small, right? Yeah. So there's, you're going to have what looks like big airs, but it's not going to make any difference because it's not a lot of water.
Okay.
Yep.
Thank you.
Mm-hmm.
So once you get above 0.18 feet, is there a reason why the outflow to elevation relationship isn't linear? Or is that just based on the geometry of whatever it is this thing is?
Well, typically you don't have linear increases in discharge anyway. I mean, these power kind of curves are what you see in stream channels. It's just a power law. It's typically what it matches. And that a lot of that has to do with the fact that the discharge and the shear stresses are related to the square of the velocity. And it goes back to the development of the Manning equation and things like that. And so we know that because it's related to the square, that you end up getting a power law relation between elevation and discharge. It's just the way it is. It's not going to be, if I understand what you're asking me is why, if you look at the storage versus elevation relationship, that's very linear. Whereas the elevation versus discharge is not linear, right? So down here, this is linear. This is a power law. And you can see that in the raw, just the data every foot. And that's just typically the shape of our curves or that.
Because it makes me think that like the outflow channel is like trapezoidal or something.
It has nothing to do with the shape of the channel, whether it was circular or whether it was, in this case, the outflow is going through a circular pipe. And as long as there's good getaway conditions downstream of that pipe and doesn't back water up, the downstream elevation has nothing to do with it. It's totally controlled by usually controlled by the inflow characteristics of the pipe. And so, that's more of a control. And again, we haven't covered that. I have not had time to cover that aspect of culvert flows. That would take probably a week to cover. It's a fairly complex topic hydraulically, but you're not going to be responsible for deriving any kind of relationship between elevation and discharge. You would be given data like this. Now, whether you fit a curve through that like I've done, power curve, or whether you decided to do a linear interpolation between 0 and 1, 1 and 2, 2 and 3, 4 and 5, etc., that would be fine. But giving you this raw data, if it was like a culvert like that, I'm going to be giving it to you, if that makes sense. I'm not going to expect you to come up with the raw data. You will have to come up with the individual detailed discharge versus elevation data, but that's through either interpolation or a power curve. Okay. Now, with that said, if I give you a weir, you are going to be, because I covered that in lecture 19, you're responsible in understanding how to come up with a rating curve or an outflow elevation curve for a weir. Okay, anything else?
Dr. Holmes,
Huh?
I have a question, but not in regards to this question. So I'm just not sure if you're done with the lecture or not. It's in regards to the final exam. I know
Okay.
it's still 2 weeks away, but I just wanted to confirm, is it still going to be that Monday after Mother's Day, which is the Monday the 11th at the same time? Or is it going to be slightly different?
Well, yeah, as far as I know, they will not change the final exam review period, schedule. I don't think there's any, I have not heard anything. So yeah, it would be in the final exam period that has been scheduled, as far as I know. Yeah, I
Okay.
haven't heard anything differently.
I just want to make sure, scheduling wise, that I don't write down the wrong day.
Yep. Okay. Well, sounds like we've exhausted the questions.
Well, I have one more real quick. That VLOOKUP, the command there in the Excel spreadsheet.
Mhm.
What's the advantage of using that as opposed to something else?
Well, I don't know. I mean, what else would you propose?
I don't know. I don't know. This is the first I've heard of that particular command.
Mm-hmm. Yeah, I don't know. I use it all the time. So I like it. So I use it a lot on a lot of things I do. Okay, any other questions? Okay, everybody. Well, listen, I'll see you on Wednesday. I would highly suggest you work through the problems for this. We're going to, I'd be glad to answer any questions you've got on Wednesday. I am probably not going to do the river routing lecture 36. I think I'm going to forego that this year just because of all the chaos with being online. And I want to leave plenty of time to leave some lecture space, some lecture periods to review prior to the final. And I haven't made the final up. I'm really perplexed as to how to do it, make it fair. And, and so still working on that aspect. So I haven't decided exactly how I'm going to handle the final yet. I will do my best to make it as fair as possible. But you're going to have to do some work on your own, obviously, to make sure you understand the problems and understand how to do things. I can't express enough how important it is to work all the homework problems and make sure you understand things. And I'm telegraphing you well in advance here. Friday's going to be a quiz based on the level pool routing method. So if you got any questions.
Can we have another review session tomorrow night like you've done, or like on Thursday night like you've done previously?
Well, I can't do Thursday night. I've already tied up and committed that night. Let me look at my calendar, see if I can do one tomorrow night.
Those are just really, really helpful.
Tomorrow night would be good too.
Yeah, I have an obligation until till right at 8:30, and I'm not sure I can be right back at my computer by 8:30. Let me think about it. It'll either be Tuesday night or Wednesday night. How about that?
Awesome. Thank you so much.
Yeah, we'll do one of the two.
Okay.
I'm a little worried about
an email.
Yeah, I will. I send it through the Canvas system. So some of you I've noticed have me blocked or something from Canvas, because I know one student had to redo their settings. And so if you're not getting these emails from Canvas, that's the way I communicate, because I don't have all your individual emails and there's way too many of you for me to individually look it up. So Canvas allows me to email you directly. And so I've tried not to overdo that, but I do send out communications occasionally to communicate broadly. So make sure that you don't have something set where it's blocking communications from me. So yeah, I'll send that out, Sean. I'll get that notice out. I got to figure that out. What my tomorrow night. I mean, tomorrow night's probably always the best because I think that's what people are getting used to. But in this case, I've got something that goes until 8:30, and I got to know if I can be back here by then. So, all righty. Well, you guys have a great day, and I'll be talking to you either tomorrow night or Wednesday in class, and then we'll have something Wednesday night if I don't do it tomorrow night. Sound like a fair deal?
Sounds good.
Okay. Take care, buddy.